Okay, so thanks. And as the last speaker, I have the opportunity to thank the organizers for putting together this great week with lots of very interesting talks. And I'll try not to let the side down. I want to talk today about some joint work with Grigoris Paouris at Texas A&M University. Okay, and it's about, so Ehrhard's inequality, but maybe Ehrhard's inequality is not so familiar to this crowd. So let me start with something which maybe is the Procopa-Lendler inequality. Okay, so now everything I'm going to do is on Gaussian space. All right, so Rn with the Gaussian measure gamma n. All right, and the Procopa-Lendler inequality here says that if I have three functions on Rn, non-negative functions, okay, and they satisfy this sort of log concavity relationship where the log of h of a convex combination is bigger than the convex combinations of the logs of the other guys. Lambda log f 1 minus lambda log g. Okay, then I have the same inequality where I take integrals everywhere. So log of the integral of h is bigger than the convex combination of logs of the integral of f and log of the integral of g. Okay, so that's an inequality about functions. It's a sharp inequality. Okay, so if I want to get equality here, then it's basically the case when f, g, and h are exponential functions. Okay, so let me maybe write it with logs. So log of f is, say, a linear function, xa plus b. Okay, log of g is the same linear part, okay, but maybe a different constant part. And log of h should be, again, the same linear part, and then the convex combination of these. Okay, so obviously with these three functions, you have equality everywhere for this one, and if you just integrate out your exponentials, then you see you have equality for this one. Okay, so this is a very useful inequality. It has lots of implications. I just want to highlight maybe two of them for today. Okay, the first one is the Kofsky inequality. Okay, which you obtain just by plugging in indicator functions here for f, g, and h. Okay, so if I take f to be the indicator function of some set, okay, g to be the indicator function of some other set, and the minimal possible h that I can take if I want this inequality to be satisfied is I take the convex combination of the two sets. So the indicator function of lambda a plus, meaning the Minkowski sum, 1 minus lambda b. Okay, and then you apply this inequality here, and you get the inequality for the measures, right? So the log of the measure of lambda a plus 1 minus lambda b is bigger than the convex combinations of logs of the measures of the sets. Okay, so that's the Minkowski inequality for Gaussian space. All right, and another nice consequence of the Procopa-Lendler inequality is it tells you that the Ornstein-Uhlenbeck semigroup preserves log concavity. Right, so what I mean by that is, okay, the Ornstein-Uhlenbeck semigroup I can write like this. PTF of x is the integral of f of e to the minus tx plus square root 1 minus e to the minus 2ty d gamma y. Okay, and the statement that Ornstein-Uhlenbeck preserves log concavity means that, okay, log f concave implies that log of PTF is also concave. Okay, this is a very useful thing because log concave functions are very nice. And if you want to do things with semigroups, then it's nice to know that you start log concave, you stay log concave. Okay, and the proof of this is just, okay, maybe I should use something other than f. So, so I suppose that psi is log concave. And I just define f, and I take x naught, y naught, and some lambda. Okay, and then I define f of x to be psi of e to the minus t x naught plus square root 1 minus e to the minus 2t x. Okay, and then g of x, g of y maybe is psi of e to the minus t y naught square root 1 minus e to the minus 2t y. And h of z is psi e to the minus t, the convex combination, lambda x naught 1 minus lambda y naught plus square root 1 minus e to the minus 2t z. Okay, and you just see from this straight away that, okay, log of psi is supposed to be concave, and it follows then that f, g, and h satisfy this condition. Right? Okay, and then I conclude that the integrals of f, g, and h satisfy this inequality, right? But what's the integral of f is exactly pt of f, sorry, integral of f is pt of psi evaluated at the point x naught, right? So then, okay, so this integral inequality here becomes log pt psi at the convex combination lambda x naught plus 1 minus lambda y naught is bigger than lambda log pt psi of x naught plus 1 minus lambda log pt psi of y naught, right? And since x naught and y naught and lambda are arbitrary, this is just telling you that log of pt psi is concave. Right? Okay, so that's just sort of a sample to get the hang of this inequality. So there's at least one problem, one reason that this is maybe not the best possible inequality for Gaussians. And it's, okay, in this Gaussian-Blumen-Kofsky inequality, it's actually not a sharp inequality. There are no sets A and B such that you have, okay, there are no non-empty sets A and B such that you have equality for the Gaussian-Blumen-Kofsky. Okay, so Gaussian-Blumen-Kofsky has no equality cases. And okay, this is not a proof of this, but maybe just a sort of an indication, right? What are the equality cases for the Procopa-Lendler inequality? They're exponential functions. And exponential functions do not look like indicator functions, right? So you don't get any equality cases from plugging in indicator functions into Procopa-Lendler. All right, and so when you have a situation like this, right, the natural question to ask is, maybe you can find a different inequality that will have equality cases, but look sort of the same. Right? And that's what Ehrhard's inequality is. Okay, so Ehrhard's inequality. So maybe I'll write, so Ehrhard proved this inequality about sets, but I want to start maybe with the functional version, which is sort of the Procopa-Lendler of Ehrhard. Okay, so now I have three functions, f, g, and h, which are going to take values in 0, 1. Maybe, okay, so I first start by defining this function capital phi, okay, which is just the Gaussian cumulative distribution function. So integral from minus infinity to x, 1 over square root 2 pi e to the minus y squared over 2. Okay, and I extend it to minus infinity and infinity. Okay, minus infinity maps to 0 and infinity maps to 1. Okay, and so the inverse of this is a function on the closed interval 0, 1 to the extended real line. And I'm going to adopt the convention today that infinity minus infinity is minus infinity. Okay, you can sort of do approximation arguments to justify this in all the inequalities that I'll write. So now suppose I have three functions, f, g, and h, that take r, n into 0, 1. And now what I'm going to do is I'm going to write down the Prokop-Lendler inequality again, and everywhere there was a log, I'm going to replace it with a phi inverse. This is the functional Ehrhard inequality. Ehrhard inequality that if phi inverse of h of lambda x plus 1 minus lambda y is bigger than lambda phi inverse of f of x plus 1 minus lambda phi inverse of g of y. Is enough? Okay, for all xy. Okay, then the same inequality holds where I put integrals, right? So phi inverse of the integral of h d gamma is bigger than lambda phi inverse of the integral of f d gamma and the integral of g. Okay, and this has equality cases, and the equality cases you get by replacing the logs by phi inverse. So phi inverse of f is inner product of a and x plus b, okay, and so on. Okay. These triple of functions gives you equality, it turns out. Okay. And you have the same two consequences, basically, right, for the same two reasons. All right, so instead of the Broom-Minkowski inequality, you get Ehrhard's inequality, which is the original Ehrhard's inequality, it's not the functional version, which says that phi inverse of the measure of a convex combination of two sets is bigger than the convex combination of phi inverse of the measures. Okay, and the second thing is that the Ornstein-Uhlenbeck semigroup preserves the property of being phi inverse concave. Okay. So now the nice thing about this is now we have equality cases, right? That was sort of the whole point for sets. Okay, and the example of an equality case is the following. So take A. Let me just look in one dimension because you get equality cases in all dimensions by just tensorizing, by taking product sets. Okay, so take A to be the set of x such that x is smaller than phi inverse of A. Okay, B to be the set of points where x is smaller than phi inverse of B. Okay, and it follows then, right, the convex combination of two half-lines is just a half-line where the threshold is the convex combination of the thresholds, right? So lambda A plus 1 minus lambda B is the set of points x smaller than lambda phi inverse of A, 1 minus lambda phi inverse of B. Okay, and so now there's an inequality about the measures of these things. So what's the measure of a half-line? Well, the measure of this half-line is just A, right? Because that's what phi was defined to be. Right? Phi is the CDF, so phi inverse is the thing that, right? Okay. So then phi inverse of the measure of A is phi inverse of little a, and phi inverse of the measure of B is phi inverse of little b, and phi inverse of the measure of this thing is the convex combination of those. And so this is inequality. Right? And you see it also in the equality cases for the functional Ehrhard's inequality, right? Because unlike an exponential functions don't look like indicator functions. Okay, but a function which is phi of a linear function, well, phi looks like this, right? And now if you take the slope of the linear function to infinity, then it starts to look like an indicator function of the half-line, right? So that's what's going on here. All right. So maybe let me just tell you what the history of this inequality was. So it was first proved by Ehrhard, which is why it's called Ehrhard's inequality, in the 80s. Okay, in the case that A and B were convex sets. Okay. Latawa in 96, I think, proved it in the case that just one of the sets is convex. Okay, and the inequality that I've written here, which is, I guess I didn't say it, but it's for all Borel sets, was proved by Borel with two L's. Okay, in 2003, so all sets. Okay, and Borel was also the one who supplied this functional version of the inequality. Okay. All right. Good. Okay, so you have these sort of parallel stories between Ehrhard and Prokop-Lendler, and it all looks, very nice. They all look very similar, but there are some points that I should make about it. Okay, so the first one is, one thing that's special about Ehrhard's inequality, unlike Prokop-Lendler, is it does not hold under a curvature lower bound. So Prokop-Lendler holds if, if I replace the Gaussian measure by, by the measure that has, say, weight with respect to the Gaussian, e to the minus a convex function. Right? Okay, but Ehrhard does not. Okay, and in fact, I would say it's not entirely clear at this point, it's not entirely clear what's a nice class of measures for which the Ehrhard inequality holds. So I'll give you an example and a counterexample. All right, so just in one dimension, I can take this measure, 2 over pi square root e to the minus x squared over 2 when x is smaller than 0. Okay? So this is just, I take a Gaussian and I condition it to be non-negative. Okay, this measure does not satisfy the Ehrhard inequality. Okay, but if I modify this measure, okay, but on the other hand, it is a log concave measure, right? It's in fact even log concave with respect to the Gaussian measure. Okay, so it satisfies all your favorite other functional inequalities, but not Ehrhard. Okay. Another example is almost like this one, but now instead of conditioning my Gaussian to be negative, I take all of the positive mass and I shrink it into a unit mass at 0. So e to the minus x squared over 2, indicator of the negative part. And then I go half a unit mass at 0. Okay, this does satisfy the Ehrhard inequality. Okay, and in one dimension, you can actually characterize measures which satisfy Ehrhard inequality by looking at the distribution functions and whether the distribution function composed with phi inverse is convex or something like that. Okay, but in more dimensions, it seems to be a bit of a mystery. All right, so that's maybe remark 1, A. Okay, and remark B is maybe related. Okay, the Prokopy-Lendl inequality is sort of very well understood by now. We have like 1 million proofs. Okay, has 1 million known proofs. Basically, you have your favorite tool. There is a way to use it to prove the Prokopy-Lendl inequality. Okay, Ehrhard inequality up until quite recently had 1, essentially. You could maybe argue a little bit, but so Ehrhard does not. So the original proof, so I ignore the ones which are restricted to convex sets. The proof of Borel is a sort of PDE proof which uses sort of maximum principle and stuff like that. So, and this proof was sort of developed and extended in subsequent years by several people. So Frank Barth and Hui, and more recently by Ivanisvili and Volberg. So I'll just call this maybe sort of a PDE proof. Okay, and so that was, so when we started this project, that was the only one. Okay, and we were sort of motivated to, okay, we had this sort of, these methods and wanted to see if they extended to this, and they do. So, okay, so today's proof. And then, independently, Van Handel came up with a very nice proof, which is based on stochastic methods. So now we have 3 ways of understanding Ehrhard, which is a big improvement compared to a year ago. Right. Yeah. Okay. So let me introduce the other thing that I had in the title, which was rho-convexity or rho-concavity, but I'm going to call it A-convexity maybe, because, all right, so let A be a K by K positive semi-definite matrix. Okay, and given this matrix, I say that a function, so let's call it J, Rk to R, is called A con either vex or concave if the following thing holds. I take the Hessian matrix of my function, okay, and then I take the element-wise product with the matrix A, and for convex, right, I want this to be bigger than 0. For concave, I want this to be smaller than 0. Okay, this is element-wise. Okay, this maybe looks like a slightly strange thing to do because the element-wise product is a slightly strange thing for matrices. Okay, but it seems to be possibly a useful notion. Okay, and then of course, let me just, so if I have the matrix of all 1s, then saying a function is 1 convex or 1 concave is the same as, well, up to having second derivatives, the same as just having it be convex or concave. Okay, so the reason this is possibly an interesting notion comes back to sort of this thing that sort of more or less I did. So in the 2x2 case, this is a result of myself with Elkin and Mosel, and then in the general case, it's due to Ledoux, which is, okay, maybe let me give myself some more space. Yes? Mm-hmm. Yeah. It's a matrix, right? So I mean positive semi-definite when I write it. Yeah. Yeah, thanks. Okay, so here's the theorem. The following two things are equivalent. Okay, J is A concave. Let me say convex. I like convex. By the way, if you're A convex, then your negative is A concave, right? So it's just like ordinary convex concave. Okay, J is A convex. Okay, and part two is a sort of Jensen's inequality for Gaussian variables. So for every function, say f from Rk, let's say from Rn, Rk to Rk, maybe I write this in a probabilistic way. So expectation of J of f of x is so convex, so this is bigger than J of expectation of f of x, okay, where x has a normal distribution with mean 0 and covariance matrix A. Okay, so the covariance matrix of my Gaussians in the bottom part is the A that is convex in the top part, right? Okay, so if you like, this is sort of a synthetic, right? This is, say, this is the synthetic version of A convexity. Okay, this is actually a trivial theorem once you have decided that you should prove it. Okay, maybe before the proof I give just a quick example. Okay, so we started out by calling this thing rho-convexity because we were interested, because originally the matrices A were just 2 by 2 matrices with rho on the off diagonal. So, example. So for a matrix of this type, A convexity, we call rho-convexity. All right, and what kind of functions are rho-convex? Well, this function, for example, okay, x to the alpha, y to the beta is rho-convex if, or maybe rho-concave, I guess, if alpha and beta are positive and alpha minus 1, beta minus 1 over alpha beta is bigger than rho squared. Okay. Maybe not immediately obvious why you'd care about something like this, but it's a nice sort of test example for this theorem, because what you get as a consequence is the Gaussian hypercontractive inequality. Okay. So maybe let's prove this theorem now. So let's say 1 implies 2. Okay, what you do is, right, I want to prove a Jensen's inequality. Okay, so I define an interpolation here, which is going to be sort of a non-standard Ornstein-Uhlenbeck, right, just a non-isotropic Ornstein-Uhlenbeck. Okay. Define it like this, where x is this thing that has covariance A, right? Of course, this is a semigroup whose stationary measure is this guy, right? It's not the only way to do it, and you could choose whatever non-centered, non-isotropic Ornstein-Uhlenbeck you like, and it will still work. Okay, and now what you do is you take a PS on the outside of this thing and PT minus S on the inside. Okay, and you differentiate this in S. Okay, and you can compute exactly what this thing is. It's PS of the trace, sort of the quadratic form of the derivative of F with the matrix A element-wise product, the Hessian of J. Okay, that's just sort of some computation with the integration by parts and all that sort of fun stuff, right? And now, if this matrix is positive semi-definite, then this thing is not negative. Okay, and that tells you that, let's see, as I move the expectation from the inside out, then this thing gets bigger. Okay, and then in the limit you get this. Okay, so that's the proof of 1 implies 2, and then the proof of 2 implies 1 is also very easy. So this is supposed to hold for every function. So I take this function, f of x is some b plus epsilon times some matrix B times x. So basically linear function, which is almost constant. Okay, and then, well, this thing has expectation little b, right? So j of expectation f is equal to j of b. And then to do the other side, I Taylor expand j around the point b. Okay, so expectation of j of f is I Taylor expand around b, so I have a j of b. Because I'm Taylor expanding around the expectation, the first order term vanishes when I integrate. Okay, the second order term is going to be epsilon squared over 2 times, if you compute it, it's this trace of b transpose a element-wise product, the Hessian of j at the point b. Okay, and since capital B was an arbitrary matrix, that tells you that this thing, all right, you know, if I want this thing to be bigger than this thing, then this thing had better be non-negative for every choice of b, right? So this matrix had better be positive semi-definite for at every point little b. Okay, and then that's it, right? Okay, so super easy theorem. Let's see, how am I? 10 minutes? All right, so maybe let's get a little bit of an idea for how you use this to prove something. Okay, and as a warm-up, so okay, so the goal, or our goal at least, was to figure out how to use these methods to prove Ehrhard's inequality. And I mean, really our motivation for this was we knew how to prove, you know, all your favorite functional inequalities using this stuff, but Ehrhard's inequality somehow seems special, so the question was, you know, can you push these methods? And it turns out you can. Okay, but maybe just as a warm-up, let me first show you the 1,000,001st proof of Procopa-Lindler inequality. Okay, this time using a convexity. So Procopa-Lindler via a convexity. Okay, you have to do a little bit of computations around 3x3 matrices, which I will omit. Okay, so here's the deal. I'm going to define a Gaussian measure on R3, which is going to be degenerate. It will only have two directions, actually. Okay, so x and y, these are each one-dimensional Gaussians. Okay, and they have variance 1, correlation rho. Okay, and z is going to be just lambda x plus 1 minus lambda y. Okay, so this is, and I take A to be the covariance matrix of this whole triple. Okay, x, y, z. Right? So this is going to be a 3x3 matrix of rank 2. Right? In the top part, it's going to look like this, and then there's some ugly things with z's, with lambdas and stuff. Okay. The variance of z is not 1. It's going to be a little bit smaller than 1. Right? It's lambda squared plus 1 minus lambda squared plus 2 lambda 1 minus lambda rho. Okay, it converges up to 1 if I take rho to 1. All right, so here's the claim, which I'm not going to prove. Okay, for every alpha smaller than the variance of z, there exists some large number r such that the following function, x to the lambda, y to the 1 minus lambda divided by z to the alpha, okay, all to the r, is a convex. Yes? Rho is a parameter. So 0. And think of rho as being close to 1. That's what it will be eventually. Okay. So now if you believe me about this statement here, then what's the conclusion? So rho-convex means that the expectation of j is bigger than j of the expectation. So let me write, so j of the expectations, which is this, so, okay, apply the inequality to functions f, g, and h to the 1 over alpha. Okay, and I get this thing, so expectation of f to the lambda, expectation of g to the 1 minus lambda divided by expectation of h to the 1 over alpha to the alpha is smaller than if I take the expectation outside, and I've left off my r, so that's going to appear on this side. Expectation of f to the lambda, g to the 1 minus lambda over h, right? The alpha and the 1 over alpha are going to cancel with an r here and with a 1 over r there. Okay, that's just the conclusion of the sort of Jensen type inequality, right, for this function j. All right, and now this is an inequality that's true for every f, g, and h, right? But now suppose that my f, g, and h satisfy the assumption of Procopio-Lindler, right, which is to say that f of x to the lambda, g of y to the 1 minus lambda is smaller than h to the of the convex combination. And now you notice that my x, y, and z are defined in such a way that with probability 1, z is equal to the convex combination, right? So this thing inside is pointwise smaller than 1. Okay, if f, g, h satisfy the hypothesis of Procopio-Lindler. Okay, and then I get this inequality about their integrals. Okay, now this is not quite the inequality that I wanted for two reasons. First of all, the inequality that I wanted had standard Gaussian measures everywhere. Okay, so this thing is not standard Gaussian. It has sort of slightly deficient variance. And the other thing is that I have alphas here, right? But of course that doesn't matter, right? Because the inequality doesn't depend on any of those parameters. So I send rho to 1, and then I send alpha to 1, and then I get the Procopio-Lindler. Okay, so in fact, you get the Procopio-Lindler inequality, and you actually get a whole family of convolution inequalities for all kinds of different parameters with the Procopio-Lindler as a limiting case. All right, so now we want to do this for Ehrhard's inequality as well. And since we know that Ehrhard's inequality, you get it from Procopio-Lindler inequality, and then all the logs are replaced by phi inverse, right? So I should just imitate the same proof and replace all the logs by phi inverse. All right, so now I define my function j to be capital phi of r of lambda phi inverse of x plus 1 minus lambda phi inverse of y minus alpha phi inverse of z. Right? And my goal is to show that for sufficiently large r, right, this thing is going to be an A convex function where A is this thing. Right? The goal, J is A convex. Okay, there's one problem here. So this thing is not A convex, right? So we're in trouble, right? A counterexample is if I just look at this function that takes x and maps it to phi of ax plus b, phi of a, phi inverse of x plus b, right? If I want a function to be A convex, it had better be convex in every coordinate individually, right? Because if I want a matrix to be positive semi-definite, it has to be bigger than 0 on the diagonal, okay? So now I just look at this thing as a function of one parameter, okay? And you say, when is this thing convex? And you differentiate it twice, and you get that this is convex if and only if A equals 1 and B equals 0. So this is convex if and only if it's just the identity function, all right? So you're stuck, right? So this doesn't work, okay? And so you have to make, it turns out, two little changes in order to make this program go through. neither of them is sort of exactly earth-shattering, but so the 2 points, it turns out, that you have to resolve. So the first one is, okay, this thing is not a-convex, right? So that seems like a problem, but if you think about convex functions, if I want to know Jensen's inequality for a function, right, and suppose it's not convex, okay, but it has some sublevel set on which it is convex, right? Then if I have a random variable which takes values in this sublevel set, then it still satisfies Jensen's inequality, right? Because the convex combination doesn't see anything that happens outside there, right? So Jensen's inequality holds if you have a function which is convex on a sublevel set and your random variable takes values in that sublevel set. Okay, it turns out that this a-convexity thing has the same property. So suffices to have J a-convex on the set of points, right, such that J is smaller than 0, okay, if, so F, the range of F, also lives in this set. Okay? And to prove this, it's basically, okay, you do the same proof as I had before. You have some sort of, I erased it, right? How did the proof work? You had some sort of flow, and your thing is getting smaller on the flow, right? So now, if you think about it, right, you have this sort of flow, and things are getting smaller on the flow. That's sort of telling you that the flow is working to keep you inside the sublevel set. And then you can continue to apply the a-convexity. Right? So you have to do some estimates about uniformity and so on, but that's basically it. All right? And this is OK if we're trying to prove Ehrhard's inequality, because the assumption of Ehrhard's inequality is an assumption of being a sublevel set of this thing. Right? The assumption that phi inverse of H is bigger than the convex combination of the phi inverses is actually the assumption that J is smaller than 1/2. Okay, so this is, you see already the first difference between this proof and the Prokop-Lendler proof. Prokop-Lendler, we proved an inequality for all choices of functions, and then you plug in the condition and you get something, right? Already in Ehrhard, the inequality does not hold for all choices of functions, right? You have to start with functions that satisfy your condition, and then you get an inequality. Okay, there was one other point, which is that it turns out that even if you sort of realize this one, it's not enough to make this thing monotonic, okay? And you can even see this if you plug in this set, the functions which are supposed to be equality cases. Okay, they are not equality cases in here. They do not. They're not monotonic in the way they should. But it turns out, okay, so PSJ PT minus S of F is not monotonic, even for very nice functions. Okay, but PSJ of, turns out you have to do this little correction, 1 minus e to the minus 2t minus s, pt minus sf might be. Okay, this thing is not monotonic, it just isn't. But if you somehow, I mean, things are changing in S, but this is the right correction thing that might make it monotonic. I say might because we don't actually prove this one. We prove this one with an extra epsilon and an assumption that F is bounded away from 0 and 1 by epsilon, and then you remove them in the end by taking the limit. Okay, but this is probably the right thing. Okay, so once you resolve those two, you get a proof of Ehrhard inequality. Let me just finish by mentioning an open problem, okay, which is hopefully going to be one outcome of this line. So problem is to characterize the equality cases. Characterize the equality cases. So I told you that Ehrhard's inequality gets you equality for half spaces, and the functional version gets equality for phi of linear functions. Okay, but it's not actually known that these are the only equality cases, although it's very plausible, I think. So that's one thing that that one would hope to do. And then, of course, once you can do that, the natural question to ask is whether there's any sort of stability around these equality cases. All right, so that's all. Thanks.